Hi, good morning. Hi, nice to see you again. So I hope your previous class was fine. I was partially also a participant of your group, but since I had some other meetings, I couldn't follow all the time. But I hoped it worked well, and I think Fuad tried to do his best. Unfortunately, I still haven't got any like class materials from him. I think he was going to give you some slides and also a sort of test concerning the previous class, but at least I still haven't got anything. I hope maybe today, tomorrow it will happen, and I will send you all the content I get, and also I will upload it over Ilias system. Good. I think we still not complete, so it takes some time. Maybe a couple of people will join us in within minutes. Let me explain our today's plan. In approximately 1 hour, we will have our first break a bit earlier than usual. The reason is I need to get my vaccination against influenza, against flu. It's mostly done here in our building at Aachen, but I need to plan like 15 minutes time to come there to get the vaccination and to come back. So approximately 9:30, we have to make a break, and probably in 20 minutes after that, we will continue the class. So concerning the material I am planning today is actually written in our whiteboard, handling forces. So there is a message, can you upload your solution part for week 3 test, right? I cannot upload my homework. Okay, let me check it one more time. I will refresh all the links. So basically, you can upload it also later. That's not a problem. Or if you are missing some homework, so if you couldn't upload it, it's also not too bad, because if one or two is missing, it's not too bad. But after today's class, I will again send you some links for both uploading and downloading. And if you don't want to wait, and if you need to upload something, you can write me direct on my email. Let me again write it here. So send it to me per email, and that's fine. So you can take a photo and just attach it to your email, and that's fine. So again, what you've done last week was the introduction to forces, to Newton's laws, and today we will exercise a bit. In particular, we'll talk about slopes, inclines, and pulleys. And I'll show you some principles, some tricks that will help you to solve problems where lots of pulleys are involved. So let me switch my camera off now, and the record is running. I think you understand what I mean if we say handling forces. So it's sort of managing forces or dealing with forces. So in German, I would say it is like Umgang mit Kräften. So as you already know, Kraft is force in German, right? And in particular, we will briefly overview what you've done last week. I will check your understanding by asking some additional questions. We will understand the difference between force and tension, because tension is not a force. So when I try to write force and tension at the same time, it never works. And then we will spend some time in talking about pulleys, and we will see how you can solve, for example, problems where multiple pulleys are involved. So something like this. So to calculate the tension and accelerations in the case if we have lots of pulleys combined with each other. And we will check it with motion and without motion, also mit Bewegung und ohne Bewegung. Okay, let us overview briefly what you've talked about with Fuad. And so first of all, we now changed our domain. So before we were in a domain of kinematics where time, acceleration, speed, and position apply, and you need just to be able to convert and to calculate them. And we learned that it works mostly through differentiation and integration. And last week we've changed the domain, and now we are in the dynamics domain. A dynamics domain means that in addition to these values, we also have mass and force, and actually tension applied. I think Fuad also explained you that there are many different forces. Maybe you know there are 4 fundamental forces in physics, right? You know there is gravitational force, electrostatic force, there is a weak nuclear force, and strong nuclear force. And that's it. There are only 4 fundamental forces. All other forces are derivatives of that forces. For example, friction force is simply a, well, mostly it is an electrostatic force. And also I'm teaching master students. We have a course, Molecular Biophysics, and in this course we address molecular forces acting between single molecules and cells in the body. And there we are talking about van der Waals forces, London forces, Kisson forces, depletion forces, and brush forces, undulation forces. There are lots of interesting molecular forces, but basically all of them are electrostatic forces. Well, actually all of them are basically electrostatic forces. Some of them, they have entropic nature, but it's not part of our course. You also talked about Newton's law. Well, let me first again remind you what we call force, right? I'm not sure if you gave some definition of force. In mechanics, we just say force is something that causes acceleration. So if there is acceleration in your system, there is some net force acting. No acceleration, no net force. So every time you see acceleration, there must be force. So we see force as cause, as the reason why things accelerate. No acceleration, no force, or no net force at least. No. So that means taken together, the forces acting on the object result in 0. And these are already things that have been formulated by Isaac Newton, and actually he did it in the frames of his work on integration. And by the way, what we learn within one class, integration principles. So Isaac Newton spent 20 years on developing those ideas together with Leibniz. So you see, these ideas are not trivial. So it took 20 years for Isaac Newton to develop the idea of integration, and then he could use it for dynamics and kinematics. Okay, and you also talked about 3 laws of Newton with some examples, right? So in fact, if there is no force, there is no acceleration. The acceleration is proportional to force and inversely proportional to the mass. And also force of action. So if you have some action, there will be also resulting reaction force. And in many cases, they will be equal to each other. Let us see how we understand those concepts and if you really got the idea. For that, let me show some example to you. If I take 2 objects, so look, these are my objects. I'm sitting here in this room and I will let these objects to drop. And the one object is actually lighter than the other, so they have different mass. So this is 2 times lighter. So if I drop them in this room where I'm sitting in, will they reach the floor exactly same time or at different times? What would you say? Please write your comment. It would be just great. So they have same size, same color, but the mass is double. There is double difference in the mass. So if I now let them drop in my room here, will they drop at the same time or not at the same time? So, thank you for the first comment. So somebody else can, would you like to try? Okay, another comment. Some more, please. Don't worry, you will not blame yourself if you are making some wrong suggestion. It's not bad. We are learning here. Okay, great. So at least I got five answers, 6. Very good. Yeah. Fine. It's really nice that our opinions like divided in fractions. So some people believe that will be same time. The other would say it's not same time. There are only 2 people now who said it will be not same time, and many say it would be same time. But let us prove it, and for that we simply use physical laws. I will not just force you to believe me. We will check it together, okay? And then you will see the answer, okay? For that, we will use the second Newton's law. And what we need to do for that, this is our object. And as this object, we let it go, so it drops, there will be essentially 2 forces acting on it. So it will be the gravity force, mg, and the air resistance force. Let's call it just F. I will use green color on it. So there will be force of air resistance, so drag force. And so now after I draw this force diagram, I will use the equation acceleration of my body results from action of several forces. So in Newton's formulation, it was like sum of all forces acting, right? So, but I know now which forces are acting, so I will draw it this way. So it will be mg minus F. Why it is so? why I have minus here? Because I need to choose the direction, and I choose direction to the earth, to the bottom, as positive direction. So this is now plus, because A in the plus direction, gravity in the plus direction, and air resistance is in negative direction, in opposite direction, outward. So that's why it is minus. Okay, so let's see, what is then acceleration from this equation? Acceleration is mg minus f divided by m, where m is the mass of my object. In other words, acceleration of my object, of any object which I'm using here, is g divided by f minus f divided by m. And that's the final formula that I should use to calculate the acceleration. Okay, and now I think everybody, you see that in spite of the fact that our bodies have same size and they have same resistance, same air resistance in fact, but still the fact that have different mass, it matters. So indeed, as some of you already commented, heavier objects will fall faster than lighter objects because there is air resistance. If there would be no air resistance, then they would all fall same speed with g. But as soon as we have even very small air resistance, there will be difference between them. So the mass matters, mass plays a role. And I think you can clearly see why it is so, or that is true, if you imagine that I'm not sitting in this room, but I'm sitting in the room filled with honey. So I will fill it with honey. I love honey, actually. And then I will swim in honey, and I will let those two balls to drop in honey. And I think you all agree that heavier objects will fall faster in a very viscous honey medium, right? So, okay, let's try another one, which maybe again might be a bit confusing for you. Let us check if you understand it. I want you now to analyze these two experimental setups. I will put some object here and here. This is my object. It will have mass of 1 kilogram. And this will also have mass of 1 kilogram. And here I will put a pulley. And here as well. So everything is totally identical now, all the same, all the same. So I will put the rope here. And so that will be sort of support, sort of table here. Of course, there will be maybe some friction in my system, or maybe no friction, it doesn't matter in fact. But look, now the difference is coming. In my setup A, I will hang a body with weight of 10 Newton weight. 10 Newton weight. And in this case, I will use my hand and I will pull the rope with force equal exactly to 10 Newton. So this will be my hand. Yeah, sorry, a bit ugly hand, but and I will apply by my hand the force equal to exactly 10 Newton. And imagine you don't see what's going on if I am hanging my mass here equal to 10 Newton, or if I'm using my hand. The question is the acceleration of this body, of 1 kilo body, this body, is it same in both cases? Acceleration A is equal to acceleration in B, or is the acceleration in A bigger than acceleration in B, or the acceleration in A is smaller than acceleration in B? So let's call it 1, 2, and 3. So let us vote. Let us give your suggestions. So what do you think? Which case will apply? Which case is true? Will they have same acceleration in both cases? Or in this case, our system will be faster? Or in this case, our system will be faster? So 1, 2, or 3, you will choose. I give you 1 minute time to think. You don't need to think about air resistance in this case, so we can ignore it actually. Okay, first answer I already got, thank you. Okay, yeah, so some other coming, good. So I hope maybe some other people will send their suggestions. Yes, good. Yes. Mm-hmm. Great, perfect. Thank you very much. We got actually again 3 different groups even, which is nice. It's good. And let me now explain what will happen here. There are 3 different opinions here. So some people said 1, some people said 2, some people said 3. And again, in order just not to say you something, we just should prove it physically, and it will be quite simple. It will be quite easy. So look, again, what we need is we use just the second Newton's law. It helps us really. What Newton's second law says, we take the sum of forces acting, right, in our system, and they cause our system to accelerate. So we take sum of masses in our system, and it will get some acceleration. So this is the acceleration we are comparing between A and B. And look, here something interesting happens. You see, there is a difference between setup A and setup B. This object on the left side, it will, of course, produce force equal to 10 Newton, which is, so it will have weight equal to 10 Newton, right? So it will have weight equal to 10 Newton. But since its weight is equal to 10 Newton, of course, it has some mass, right? So that means in our system, we have actually 2 masses. So this mass and this mass. So this is 1 kilo, and this is also approximately 1 kilo, okay? So basically, the mass in our system is sort of close to 10. So acceleration will be sum of forces divided by sum of masses. So in my case A, sum of masses is approximately 10. So I would say F divided by 10. What about B? Is my hand as heavy as, well, let's say 1 kilo? Actually, not necessarily. It is lighter, and moreover, I'm pulling with this force. So it's not weight of my hand, it is my pulling force equal to 10 Newton. So that's why, effectively, in the case B, the overall mass of my system will be less as compared to the first case. So it makes difference again. So using my hand, which applies this force, makes a difference, because effectively you can say the mass of my system is less. So in the second case, the acceleration will be sum of forces divided by maybe, let's say, 7, even if I take my mass of the hand into account. And that's why in this case we probably should answer, it would be more correct actually to say that acceleration in a case in a B is larger than acceleration in case of A. And again, it actually follows from Newton's second law. I know it is a bit of a confusing example, but if you think about it intuitively, I think you will agree with that. It might take some time. So it makes difference if I use weight of 10 Newton, but it brings also mass with it, or I'm using just my hand to make this force with my hand. It makes difference. Okay, I am still glad that I could confuse you a bit, because certain physical intuition is required in solving physical problems, and this is what we are exercising together with you, because just knowing set of formulas for problem solving is not enough. You need to be able to analyze and to know how you apply formulas in the right way, in the correct way. And this is what we are doing now. So the answer is 3. Okay. Before we go ahead to some problem solving, let me explain the difference between force and tension. I think you all know that force is a vector, right? Because force causes acceleration, and acceleration is basically in the same direction as the dominating force, as the net force. So one vector, the force vector, causes acceleration to happen, and acceleration is a vector as well. So, but what is tension actually? Look, if I have some rope or some object, and if I pull it, there is a tension in this rope, and I feel it. Tension is there. But is it a force? It is not, because force must have direction. But if I ask you, okay, if tension is force, in which direction it is in this rope? If you say in the left, then it's not, because it's not accelerating to the left. If it's to the right, no, it is not accelerating to the right. It's not moving. So that means acceleration is not a force. But what is, tension is not a force, not a vector. But what is it then? So what is tension? And tension is, look, if I draw it, This is our rope. And if I hold it from both sides, then this hand will feel some resistance from the rope. This will be tension. And this hand will also feel some force here, and this is also tension. So how comes that it is acting in two directions at the same time? And the answer is yes, it can be like this, because tension, strictly speaking, is a tensor. Some of you have been already from the beginning of our class, and you remember that we, at the beginning, talked about difference between scalar, vector, tensor, supertensor. Let me repeat it briefly because there are a couple of new people here. Scalar, we describe with one number, it has no direction. Vector, we need, for a description of vector, we need more than one number. It could be 3, 5, 10, 100, or million. Doesn't matter. It will be then 11-dimensional vector or million-dimensional vector. It doesn't matter. So it's just some entity for which we need more than one number. And we describe vector as a row, as such thing like A1, A2, A3, A4, and it can be quite long. But in some cases, this notation is not enough. It cannot describe what happens. And we need to go to the next level of complexity, and we need to introduce a new value, which is called a tensor. Tensor is a combination of vectors. So in fact, tensor is a sort of matrix in mathematics. So it is A1, A2, A3, A4, quite long, but also B1, B2, B3, and so on. And it can be also quite long in this direction. So tensor mathematically is sort of matrix. In other words, a tensor is a combination of vectors. We need to use several vectors. And tension is a tensor, actually. As you will see later in your technical mechanics course. And sometimes you need even to combine different tensors to get even more complex value, and it will be called a supertensor, which is used in some applications as well. So, in other words, tension is combination of vectors. In our case, it's quite simple. It is a combination of two vectors in one direction and another direction. So, and this combination is tension. For problem solving, you don't need to know it. You don't need to use it explicitly. But please keep it just in mind. For most of problem solving, we will treat tension as a normal vector. But please keep in mind that it is not a usual vector, it is a combination of vectors, right? And that's why it is not strange that for some object tension is in one direction and for another object it is in the other direction. It is quite normal, but it is same tension. And today we will talk about pulley problems where we will talk about tension along the rope, and then you will see that in every point of the rope, tension may be same everywhere, or it might be different along the rope. And we will talk about these issues as well. Now let me ask one more, maybe for your ideas. It's such a practical problem, okay? So imagine someday you are driving some beautiful car, not the car which I'm drawing is pretty ugly again, but imagine you are driving some very beautiful car. And you're stuck because the ground is like a swamp, like boggy, and you cannot move forward. So your car is jammed. And you see there is a tree here. And you have a rope actually in your hands. The rope is long enough actually, but you are alone actually. That's a problem. You don't have any additional, like sort of additional motor or additional people who could help you. So what do you think? How would you need to apply your rope to free your car, to set it free? What would you do? Can somebody explain? Does somebody have maybe some idea? What would you do in this case? You have a car which you need to move forward, and you have a tree and you have a rope. But what would you do? This is just very normal tree. What would be the best way to act here? Somebody wants to comment? If you have some ideas, you can raise your hand and I switch your micro on so that you can suggest something. Okay, good. Okay, go ahead. Yep, come on.
What we can do is we can tie the rope around the tree,
Okay.
and then we can the rope must be wound around the wheel which gets the power.
Oh, okay, here, right?
Yes.
So you mean driving wheel, right? So it will be
Yes.
this, okay.
Yes. So when we rev the engine and the wheel rotates, it will take the help of the rope and the car will move forward.
Oh, nice idea, nice suggestion. Yeah, I understand. So actually you will use it in a more productive way. So because otherwise the wheel rotates, but it has no connection to the ground.
Yes.
And you will attach it to rope, so it will pull the rope. Very good.
Yes.
Okay, beautiful idea. Thank you very much for that. Thank you. Nice idea. Maybe we have some other ideas, or so just let us make other suggestions. I found it a very good solution, but let me make some additional troubles to you. So let me play like devil's advocate, and let me make this rope short enough so that you can only here attach it to the tree, but you cannot attach it to the other wheel. Okay, so let me make it more hard for you, because your solution will work, I think. But what if the rope is shorter? What if we only can attach it here and here? To make a pulley, so here some suggestions. Thank you for this idea. Yeah, so make a pulley system. Well, it may work if you have a very nice, very smooth tree, so that you can pull it in the other direction. But I'm a bit afraid that a usual tree would have a lot of friction force, so it will not help you much if you put the rope, around tree and you pull to another direction. I'm not sure it will help you much. But thank you again. This is also a good idea. Let me actually tell you one more idea, which is also quite nice, and it works pretty well. And this idea is to use the power of tension. The thing is that if you make this rope, if you make a big tension in this rope here, large tension between this point and this point, And you see that it will be almost straight. The rope will be like a string, right? So it will be very tightened here. And what you do is you press your rope in this direction with your body weight. So just like this. Interestingly, from physical laws, it will cause very big tension, much greater than the force you can apply with your hand. Let me show it on the drawing. So this is your rope, and there is some tension in your rope. Let's take some point, and this is tension. And if I now make some displacement here, if I pull my rope downwards and I make displacement, it's like not away from the car, but sort of perpendicular to the rope. In this case, we will produce tension which will be much greater in magnitude than the initial tension was. And this is a nice trick that can be applied if you have such a case. So not pulling the rope, but making big tension in the rope and then pressing it downwards. And you will see suddenly, you can do it even with one hand, the car will start moving. And it will look like a wonder actually for many people that, that the car will start moving. So you use just the tensor properties of tension. So you just need to apply it in the right direction. And in this case, you don't need to use much force. You can, by the way, if you have this opportunity at home, you can try this method, maybe not with the car, but with some other object. Just do this experiment at home if you have time, maybe on weekend. Put a rope between two objects and just pull it down, and you will see the force in the rope will be really big. You can do many things in applying force this way, downwards. Okay. Now, I think we are still at the second point, first and second. Do you remember how, what's the word, the German word for tension? Maybe Fuad already explained, it is Spannung. Yeah? So please just also notice these words. These are important words for us. They will appear in problem solving soon. So Kraft is force. So it's die Kraft or eine Kraft. And tension is also feminine. It is Spannung. And also die Spannung or eine Spannung. And here there is a sort of ambiguity because also for voltage, in German they use the same word, Spannung, elektrische Spannung. So this is the voltage term. And it can be confusing because if they say just Spannung, you never know what exactly mean. Spannung may mean tension in the rope. Spannung may be my psychological tension. So that means, for example, I say, ich bin gespannt, ich warte das mit Spannung. That means I am quite of excited about something. I have my psychological tension in me. And electrical voltage is also Spannung. So how would you differentiate? In order to make it more precise, we can use another word, which will be Zugspannung. It will be more mechanical, more precise. So you can use just Spannung, or you can use Zugspannung. Zugspannung. Sorry. Also feminine. Zug means also pull, to pull. It has also lots of meanings in German. It's also a train and also lots of things. But Zug also means if you pull something, ziehen, pull. So that means pulling tension that appears due to pulling, Zugspannung. Okay, so we tried our physical intuition in solving physical problems, and we discussed a bit the difference between force and tension, and we remember that tension is something inside the rope, within. It is a tensor. Just to finalize this part, let me give one more explanation about tension. I think it's quite nice. Look, I can say force is something that tries to accelerate objects. Tension is something that tries to destroy objects. I think it makes sense. So if you just apply force to something without producing tension, it will make an object to accelerate, for example, a ball. But if you have tension in a ball, for example, by pulling it in opposite directions, you are trying to break the ball, actually. And if you're strong enough, you can really rupture it. So we can really put it like this. Force is accelerating and tension is rupturing. So this is the way how we can also explain it. Now I have prepared a couple of slides for us. I will announce a couple of pictures, and then in 5 minutes we need to start our break. So I need to get my vaccine. And before I go, I want still to give you one little problem to solve. Okay, just that you don't feel bored. Let me first start my PowerPoint presentation. What you see now on your screen is typical setups you must be able to solve in your tests. So when we have midterm and the final test, and those are most standard, most typical setups, and we need to feel comfortable in addressing all of them. So you see there are different arrangements of bodies, and we will today and next time we will exercise quite a lot in dealing with such cases with friction, without friction, with massless rope, and with rope that has mass. And it will be first easy, very easy, then it will be harder, and in the end I will show you some very advanced problems which are quite sophisticated. And also this PowerPoint I will send to you today after the class over both Ilias and our EduPage system. So about forces we talked a lot. So I explained about tension, that it is a tensor that can act in opposite directions at the same time, and it actually represents the third Newton's law, so action counteraction principle. For a while we will treat all bodies as being point-like bodies. We will not talk about center of mass and force distribution and rotational effects, and they will appear in the second half of this course. For now, we will assume that all forces act on your body in a sort of same point. So we don't need to consider arm levers, so torques that appear in the system. We simply apply forces on your objects, and we assume that forces are all applied sort of in the same way. So we simply can add them as simple vectors in a vector-like manner. In any problem solving, it will be important for you always to draw a force diagram. This is necessary. So, for example, in this setup, you always please need to specify first which forces act in your system. This is very important. Even if you say, come on, it's quite simple, I just can get rid of it, it's no problem. Please do it, because it helps. Sometimes you can forget one or another force, and it makes your whole calculation wrong. So please take time to handle these pictures and to draw forces, okay? You don't need to take any photos, whatever, of your screen. I will send the presentation to you, okay? So don't worry about that. So in this case, in this particular setup, I would say there is a pulling force, there is a friction force, there is a gravity force, and there is a normal force, which is equal to gravity force because my box is not moving in this direction. That's why I already know that these two forces are equal to each other, right? And then you don't need to pay attention to the equations here. We can, for a while, ignore them. It is just to explain that please always make a force diagram. In German, it is called das Diagramm für Kräfte oder Kraftdiagramm. And in your today's homework, you will have one or two tests in which you need to make this diagram of forces. And now I have to start our first break, but before, let me use this time. If it takes longer than expected, I hope in a quarter hour I will be ready, but if it takes longer, I want you to spend this time not useless, and that's why I want to give a problem solving to you, which is quite nice and teaching us still a lot. Let me show. Here's the problem I want you to think about. I want you to try to solve. Here I will maybe draw a little bit about this setup, and then I have to leave. It is a system which looks like this. You have a person sitting on a board. Oh, sorry. And there is a pulley here, and the person can pull himself upwards, actually. He can apply his muscle tangent, just muscle work, to pull himself upwards, right? So, okay, I have better drawing. So now please think about this, and when I come back, let us discuss. Meanwhile, we can send your answer to the chat window. So what is your answer? What is acceleration of this person? If you take this information into account. It's not simple, it needs some logical thinking work. But I want to challenge you a little bit to give you this exercise, and let us see how it works, okay? So I will switch the camera off for a while. We see us in approximately 15 or 20 minutes. And if you want to drink some coffee meanwhile, of course, you're welcome. See you in, let's say 15 minutes. See you. So I'm back again. Well, I did it. It was actually quite nice. So that was just a small injection. And so this is what we do here in Fachhochschule from time to time against influenza, some vaccination. I'm not doing it every time, but just from time to time. So, do you think that was a bit a difficult problem? I haven't got any comments so far, any answers. Is it because you found it a bit hard? Are there maybe still some, some not solutions, but some answers? Okay. Okay. Yeah. Thank you. So I know that could be confusing. That's totally fine. Please don't feel upset. It's not such an easy problem indeed. Yeah. So it's totally normal that you feel maybe a bit confused. I want to use this example to show you the importance of making force diagrams, because I agree with you. If you just check it this way, how we did it, it looks somehow strange. You don't know how to put solution. You know that it is certainly about Newton's laws, but why and how, it is still not clear. Let us do it together, okay? And you will see that it's actually quite simple. So for that, let me again choose another program where I can draw better. I need just to open my drawing program. Yes, and let's do it in a in an expected way, in a systematic way. So I told you before, it's very useful to make force diagrams. First of all, what are masses in our problem solving, in this particular problem? What are objects? The rope is not an object because it has no mass, so we say, okay, the two objects are a painter and seat. Okay, let me do it. So this will be my painter, and this will be my seat. Okay, now what are forces acting on painter? Let us just put them together. So, of course, painter feels some gravity force. Let's draw it. M painter G. What else? Its hand is holding rope, right? The rope. That means he will be pulled upwards by the rope. So upwards, there will be tension, T, in the rope. And since he is applying force on the seat equal to 392 Newton, the seat applies the same force on him back, right? So reaction force. So from the seat is also upwards, right? So it's logical. So 392 Newton from the seat. So that means we did the force diagram for painter. These are three forces that we need to take into account. They are acting on painter. We are not interested in which forces acting by him, but on him always, on the painter. Gravity, tension, and reaction force from the seat. What about the seat itself? We can do it in parallel. I think you have an idea what we have here. Forces acting on seat. Of course, it's again gravity, right? Because our seat has some weight, some mass. Oops. So it's downwards, right? M seat G. It's weight, it's Gewicht, we say in German. Gewicht. So then downwards, the seat feels some force from the painter, right? So the paw from a painter is pressing on the seat. So that means we have also force from painter, which is equal 392 Newton from painter. And as you see from the drawing, the chair is also directly connected to the rope. So that means there is also a tension force that pulls the chair also upwards, because tension only can pull. So it feels also T force. So now after we did this force diagram for the painter and from the seat, these are two masses we have in our system, two objects. Now we are ready to decide about which direction we will choose as positive. And I think Fuad has explained this, that every time you need to decide by yourself if your positive direction will be, for example, in one direction or other direction, so upwards or downwards. I would say I would choose, yeah, whatever. So let me choose this positive this time. But you can do downwards. It's up to you. So this will be my positive direction. I need to apply it because I need to come from vectors to their projections, to some numbers which I can calculate. And that's why I need to, because all these things I drawn, they are forces, they are vectors. I cannot calculate them as vectors. I need to convert them into scalars, into projections on this axis. And so first step was making force diagram. Second step was to decide about positive direction. Third step is to apply second Newton's law, which postulates the sum of forces applied on the object cause this object to accelerate, right? So F is equal ma. So on the left side, we will write forces acting, and on the right side, we will write the acceleration. So let's take the painter first. Painter. So look at the diagram and look at the positive direction, and let us write together the equation for forces. So positive direction, we have tension, that means plus tension, plus this reaction force, 392 Newton, 92 Newton. Now minus, right, because it's in opposite direction, minus weight of the painter, mpg. Okay, that was it. We have accounted for all three forces, equals, now we're in the right part of the equation, mass of the painter, mp, is accelerated with acceleration a. This is what we are looking for, right? This is what we are searching here. But this is our unknown value. So can you please do it now for the seats? just give it, you don't need to show it to me, but I want you to try it by yourself, and then I will do it too. So it's better if you do it by yourself, okay? So do it for the seed, please. Again, you don't need to send it to me. You do it for yourself, right? So to check yourself, to control yourself. Okay, I think it worked, right? So again, we have T positive, so it's upwards here. We see it positive, T, and that's the only positive value, right? So now we have minus 392 minus msg, and this results in acceleration of the seed. Seed get some acceleration. Let me comment a bit what we see here. First of all, because this is the same rope which connects the painter and the seeds, we say that both T values are same because it's same rope and it has same tension everywhere. So that's why we don't need to use T1, T2, T painter or T rope. T is same. And also acceleration is the same. Why acceleration of them is same? It's also logical, right? Because they move together, they move in the same way, they move together. So that's why the acceleration is also same. So now we have a system of equations which we need to solve for A. What would be a good way to do it? It's quite easy if you see there are two equations, one and 2, and if you simply subtract 1 from 2, you can be able to get some nice solution, because if you subtract 2 from 1, then you will get rid of T. It will disappear. So let's subtract the right parts from each other. So T minus T is 0. Then 392 minus 392, it means plus 392. Then we have minus MPG minus MSG, that means plus MSG. So that was right part. Left part, MPA minus MSA. And now you have actually only one unknown in your equation, which is A here. And if we solve this equation for A, I think we'll get the answer, which will be probably close to 109, or depending on G value, but it will be something close to 1, maybe 1 point something meter per second squared. And this is the answer to our problem. And you can now, if somebody asks you to find tension, it will be also quite simple, because you just say, okay, I found A, it is equal 1 point something, and then you put the values here and you can find T, right? So it should be simple for you. I think I solved it once, but T was 479 Newton, I think. Just to let you know. Okay, I will solve this writing sheet for you, and I will send it to you today. Let me save it. So today is 24th. 20, and it's our first picture. So I will send this script to you so that you will have it. Actually, okay. Would you agree that after we did it like step by step, after we split it into simple parts and we did it carefully and slowly, in fact, the problem wasn't difficult, right? So it is a bit confusing, but if you do it really step by step, slowly, it is not hard. It is sort of okay. And that's why our goal will be to exercise, to solve more problems like this, so that you feel comfortable that you can solve them in a nice and easy way. And so my main goal is that you get certain self-confidence in solving problems. You know how to do and what to do. Let us jump back to our PowerPoint presentation again. And let us now address next point. Just a little exercise. Again, you don't need to send the solutions to me, but please do it by yourself. How would you solve this problem? Please check it. Please do it. Again, let me remind you what you need to do. So this algorithm should remain always. Please always keep it. So first step you do is you draw the forest diagram. Here in your system, there are two bodies, two objects, and you do forest diagram for each of these bodies. So for M1 and M2. Then you decide about which direction is positive. So what your x-axis will be. And y-axis. Maybe you need, maybe you don't need y-axis. And after that, you write second Newton's law. Oops. And you solve it for A. Oh, just please do it. Let us say 5 minutes should be fine. Good question is, by the way, if there is friction or not. Well, let it be without friction, okay? So just for simplicity, so let's put friction to 0, so no friction. So I hope it worked, at least to a certain extent. Let us check step by step. So first of all, we draw force diagram, right? So let me show how it could be done. For example, like here, we make a force diagram for the body 1 and for the body 2, right? So where's my laser pointer here? So this is for the body 1. There is what are forces acting on mass 1? It is our force that acts on it. There is a reaction force from body M2 because you agree that it will a little bit oppose the force F. Because if it would be no mass M2, it would be accelerated, but there is some inertial force from mass M2. And in the vertical direction, it is the gravity force, which is precisely opposed and compensated by reaction force N1. So this is our force diagram for the first body. And for the second body, actually, it is not the force F which acts directly on this body. It is mediated by this mass. So actually, this body M2 is not feeling directly F, but rather it is feeling the force that is given by mass M2, M1. So this is here. And here is the other two components. So this is what we expect from you as your initial analysis at any problem solving. And you are getting points for that. Please don't forget this. We are checking your solution, and if you've done this analysis, you are getting points. So if the problem brings you 10 points for this drawing, you will already get 2 or 3 points. So then you decide about which direction will be positive, for example, to the right, and then you write the equations of motion. Newton's second law, let me write. I will not solve it to save our time, but I will write the equations, of course. So for M1, let me use another program maybe. Okay, I'll still try. It's a bit difficult to write in PowerPoint. So what do we see here for M1? No, I will do it like this for M1. What is the sum of forces acting on M1 in x direction? It is F minus this, let me call it reaction force, this R, reaction forces, minus reaction force, and it causes M1 to accelerate. For the body M2, again, what is sum of forces acting? Okay, it's simple. It is the force R that makes it to accelerate. So R is equal M2A. And as you see nicely, again, if we add these two equations to each other, then we will get F minus R plus R, which is 0. Okay, let me write minus R plus R equal to M1A plus M2A. In other words, R and R will cancel each other because according to the third Newton's law, they are equal, and we will get the solution in the form F is equal A M1 plus M2. In other words, acceleration is equal F divided by M1 plus M2. So this is the way how we expect you to solve such problems. I understand that some of you might be wondering, why don't we put it simpler? So if just consider these two bodies as one body because they are touching each other, and simply applying F is equal m1 plus m2 multiplied by acceleration, and you get the same answer. Well, yes, in this case, you dare do it, you can do it, and it's not false, and it's a shorter way. But in many cases, it would be more advantageous to consider each body separately, because in some cases, you cannot be sure about the exact interaction between these two bodies, and you will be on the safe side if you do it for each body separately. Yes, it might take a bit longer time, but you make it in a more systematic, analytical way. If you are 100% sure that your bodies move in the very exact same way, then of course you can apply the simplified way and you get the answer, and it is not wrong, and you will get also all points. But only if you are sure that you can consider both masses as one entity, as one thing. Everything is okay? So actually these are basic things. I hope that you feel now more certain about our algorithm. This is what I'm trying to impregnate into your mind today. So this is the root. I want it to make like automatic in your mind, that every time you're solving dynamic problem, you always follow same way. You use the same algorithm, because for every point, for every single number, you are getting points, and I want you to get maximum amount of points for your solutions. I already explained it once, that in your problem solving and in your tests, midterm test and final test, we are not very much interested in the answer itself, in some number you get. It might be even wrong. We are very much interested in how you solved it, what your solution was. Did you use the right thinking? Did you use the right formulas? Did you apply them in the right way? This is what brings most of points. The answer itself, even if it's a bit wrong, it's not too bad if you have the right solution. Okay, so please be aware of it. And one more thing again to remind you, if you only write your answer and you don't show your solution, you're sometimes getting 0 points, because many physics teachers do not recognize if you have just lonely answer. I think it is sort of fair, because sometimes I observed that some weak students simply looked the answer from their neighbors and they just put it there and they say, look, I have it in my mind, I have this answer. But I think it's not fair, right? Because one student is solving it and getting the answer, and the other student just looks up and says, oh, okay, this answer, and writes it, say, look, I was the first. It's just not fair. That's why we want you to focus on solving it and showing your solution. Okay. Now we will solve one more problem, then we make a very short break, and after that we will talk about pulleys. And I think it will be nice and interesting for you to learn how you handle pulley systems, because this is something you might have not learned yet. In some schools, they don't address this problem, and I want to explain this, and I think you will appreciate the beauty and easiness of handling pulleys. But before, I would like us to solve yet one more problem together. Let us exercise this algorithm we discussed before. Let us apply it for this problem. We have some car on a very slippery, frictionless incline, and we are interested in calculating acceleration of this car. Assuming the engine is off, so the car is actually just standing there, but because it is so slippery, so, have no friction, of course it will slide down slowly. Even if the driver tries to apply brakes, still the car will go downwards. So what will be the acceleration of this car if I give you the angle? And if I say the slope is 0, so the slope is theta and the friction is 0. How much is the acceleration? Please calculate it by yourself. I give you 5 minutes again, and maybe if you can send me your answer, that would be great. And then we check it together. Please don't wait for me to give you the answer, because this is not the best way to exercise. You only can exercise and you only can learn new things if you try them by yourself. Yeah, very nice. Thank you. I'm already getting some answers. They look good. Very good. Fine. But still, let me wait for a couple of minutes for the other people to join to finalize their calculations. So I see that this works. You did it good. Again, the problem by itself is quite simple, of course. So the main goal is to automatize, in your mind, to automatize the application of those steps. First step, drawing forces. Second step, defining axis and positive direction. Third step, applying Newton's law to them. And fourth step is to finalizing your calculations. And I see it works pretty well, very well with you. That's great. Maybe a couple of more answers, please, because we are 15 people in the group and I only got a couple of answers, maybe some more. Also, if you have still troubles with it and if you don't know, that's also an important signal to me, okay? If I'm only getting information from people who can do it, then I say, okay, we are fine. But if there is there's somebody in the group who has troubles and I'm not aware of it, this is not good, right? So please also give me signals, and please let me know privately if you still cannot solve such problems, then it will be good for me. Thank you. Again, you will not blame yourself, right? We are learning, and if some answers are wrong, it's not bad. That means you will learn something today. Emmanuel, yeah, I think the question is actually, just imagine this, sometimes it helps. So you just think about some slope, right? And on the slope there is a car, and you have suddenly no friction on your slope. So I think in this case we will have some acceleration, right? So because there is really no friction, the car should slide down. And it will slide down, I think, depending on the slope, right? Depending on the angle. So that's why acceleration will be actually not zero, but we can find this acceleration. Maybe it will depend on the mass of the car, maybe on the angle, or maybe on something else. So that's our goal, to find it by applying these 4 steps. Okay, yeah, that sounds better. But look, okay, let us. I got some answers. Again, my kind request to everybody to really to send me your answers, because I just want to get feedback from you to see where you are. Because if I see what's going on, I can help you better. If I assume everybody is perfect, then I say, okay, let's go further. Everything's fine. Just not to make it boring for you, of course, I will move forward. But if I see some of you need more help, I will be able to help. Okay. Yeah, thank you. So let us check now together. So what we do, we make a drawing, right? So make some nice forest diagram that may look like this, for example. So you can just put, this is your car, and you say, what are forces acting on your car? And here you will see that there is a gravity force, mg, but since the car is standing on the ground, there will be reaction force, let's call it n, from the ground, right? So, and it will be always, it is a normal force. It is a force that is perpendicular to the ground. So these are 2 main forces that are acting on our car. This normal force appears as a result of gravity component acting towards the ground. And if you put your axis this way, x, y, then your car will move both in x direction and in y direction. And it's sort of a bit not so convenient, so to put axis like this. It is more easy if you put your axis this way, so that the x-axis will follow the slope, and the y-axis will be perpendicular to the slope. Why it is so good? Because in this case, you have no motion, no acceleration in one direction, in y direction, so you can get rid of y-axis. You don't need this y-axis. You can totally ignore the y-axis.
So now we are only interested in x-axis because only along the x-axis something happens, so acceleration takes place. And let's now see what causes acceleration, which force. We know it is mg that causes acceleration, but is it complete mg force? No, only part of it. So this is the whole mg force, but it is not entirely responsible for acceleration. Part of the mg force in this direction, this component, doesn't play any role in accelerating the auto, the car. It's sort of unimportant for us. Only fraction of this force, this one, only this fraction, is important for us. And this little arrow is mg sine of the angle from the triangle. This is the force that actually causes acceleration in x direction. So now let's draw the Newton's second laws for both directions. So for y direction, we said nothing happens. That's why we sort of can neglect it, just put everything to 0. And here we have the equation that we require. We are searching for acceleration. And we can see that acceleration is actually simply, we can exclude mn is away. And what remains is acceleration is equal g multiplied by sine theta. And this is the answer. Actually quite nice and interesting to see that in this case, the mass of the car does not play any role, since we have no air resistance and no friction, right? Because of that, we are not, the mass cancels, and the equation looks like this. So the acceleration of the car will only depend on gravity constant, on gravitational field, and on angle, on the angle. Okay, very good. So in our midterm exam and in the final exam, of course, we will have a little bit more difficult problems. So these are very basic, very simple problems, just to exercise the methodology. And in your final exam, or no, in the midterm, we will have a little bit sort of next level problems. From easy, we would move to middle, average difficulty. And this is what we're going to do today. After the little break, we will address some more complicated problems involving pulleys. I want you now to have a rest for 10 minutes just to relax, and so that in the final section of today's class, you can stay concentrated more and you appreciate the beauty of dealing with pulleys, with multiple pulleys in physics. So let us make now 10 minutes long break, and after the break, I will explain you about pulleys. So see you in 10 minutes. Strangely, I'm not getting the answer here. There's a problem with interface a bit, but still, please try to send your suggestion, maybe. So again, what we see here, which actually force acts downwards. So what's the force pulling the system downwards? Well, this is this force, this is 1. So this is the weight. So we have just 1 downwards here. And it is opposed by the system, and what we have here is T and 2 times T, right? So our equation looks like this. 1 is equal T plus 2 times T. So if we solve this equation now, T will be equal 1/3, 0.3. Okay, so same way of thinking, same thing. So let me open it. 1/3, 1/3, 1/3. Okay. So what about next one? I really want you to exercise, right? I want you to get tangent is equal at all points in the string. Yes, exactly. So this is what I want to thank you for repeating it. Thank you for asking. Let me again emphasize, everywhere, as long as we have same rope, this rope has no mass. If it's not given to us, then we assume that everywhere where this red rope there, tangent is always same. So all red points have same tangent. It is sort of X or T, whatever you call it. So what about this left setup? Do you have any idea? So again, let us do it same way. Count all forces acting downwards, and they are equal to all forces acting upwards. T, 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 T. But how much is this T? Okay, so thank you for answering. Okay, we are getting different answers. So let me show, just to make it more clear. So downwards, we have T. You see, it's here pulling downwards. So it's T plus 1. So we have 1 here. T plus 1. And that's it, because all other objects, they have no mass. What we have upwards, so here we see 2 times T here and 2 times T here. So that means 2 times T plus 2 times T. So that means 1 is equal 3 times T. T is equal 1/3, 0.3. What about the right one? Thank you again for responding. Let's check it. So this is all 1/3, all of them, 1/3, 1/3, and so on. What about this one? Again, T plus 1 equals is 2 times T, 2 times T, T. Okay, 5T. So 1 is equal 4 times t. T must be equal 1 over 4, 0.25. Let's check our solution. Okay, indeed. So here tangent is 1/3, and here is tangent equal to 1/4. Okay, so I think it's quite simple and quite nice to use this way of thinking for solving such problems. We are now in the simplest domain. Our rope has no mass and our pulley has no mass. And that's why everything looks so simple, even surprisingly simple. In the future, it will be more complicated, and we can make our rope having some mass, and we can make our pulleys to have mass. And that will be more interesting, but this will appear later in this course, in the second part. Okay. I think that was it from fully operational principles. And the final thing that we need to do today is a very simple so-called Atwood machine, which I think everybody know already. So before, we only addressed pulleys that are not moving, are at rest. And now let us think about pulleys that are moving, that have some movement in them. And the simplest setup we may imagine is called Atwood machine. This is what it looks like. Again, please be aware, friction, we have no mass in the rope and no mass in the pulley. So the only two masses we have here are M1 and M2. And here, again, we need to apply same methodology, same algorithm we applied before. That means if you need to find acceleration in the system, you need to consider both masses independently on each other. What are forces acting on M1? Make a force diagram. What are forces acting on M2? Making force diagram. And deciding about your direction. And then you solve it by using Newton's laws. You don't need to solve it by yourself. Let us do it together, because here there is a little trick I want to show to you. So first of all, about force diagram. I think it's quite clear. Forces acting on a mass M1 are gravity force and tension. Forces acting on the mass M2, again, gravity and tension. And here, tension is same, but gravity is different in this case. So now we need to decide about positive and negative direction. And here I want to share some interesting trick with you. Before, we only talked about up positive, down negative, okay? Or, for example, up negative and down positive. Well, this you can use always, but there is more easier way to make it. In pulley problems, you can make your rope your axis, because all motions take place along the rope, because it is the rope that moves. You don't need any other axis except rope axis. So you have only one axis, which is your rope, and it can be curved. That's a bit confusing, but you can use it. Your axis can be curved. That means I can choose my positive direction like this, so it will follow the motion in my pulley. So this will be my plus direction. You see, it is not up, it is not down, it is just simply following the motion of my body system. And what if I don't know in which direction my system moves? Maybe it moves this way or maybe this way. So if I have two bodies, maybe it moves like this or maybe like this. It doesn't matter. And you can just simply put this as your positive direction and make all your calculations. And if in the end you get negative answer, it means that your direction was sort of wrong. But it's not bad. It's not a problem. It's not a mistake. You just choose any direction and you check the answer. And if you get negative acceleration, then it means your system moves in opposite direction. But it doesn't change anything in your answer. Actually, that's why this trick is to use these as your axis. So you can try to use it and it looks quite nice. For example, here, I would, for example, say that if we write now the system of equations for mass M1, I would write tangent minus M1G is M1A. And for mass M2, I would write M1G or M2G minus tangent is M2. Oh, it's over now. Okay, I will project it here now. So you have now it on another screen. Just a moment. Yeah, sorry, because the tablet is now there, so it needs to be charged. So that's why I have to jump to this screen. So, and here you will have, and I cannot really draw, but I will try. Okay. Okay. So M2G, right? And then you solve it as we discussed before. So basically, you can, for example, add one equation to another equation so that tangent and tangent will cancel, so that your result will be M2G minus M1G, because it's minus here, equal M1, oh, sorry, it's not G, it's A. Yeah, thank you. A. M1A plus M2A. A. And from here you get A equal to G M2 minus M1 divided by M2 plus M1. And so this is actually the answer. Okay, so that's sort of problems it's a bit too easy for midterm. In midterm, you must have a little bit more difficult problems, but if you use same way of thinking, you can solve also more complicated problems, of course. Okay. Today, after the class, I will send the video record to you. I will send, oh, let me see, it's still running. Yes, it's still running. Good. I will send the PowerPoint slides to you, so this script to you. And you will get our next test, which I will name test 6, because I'm still waiting for 5th test from Fuad. And the 6th test will be quite short and easy. It will consist on 3 or 4 problems only. And in that problems, we will only have things that we discussed today. It will be about Atwood machine, it will be about pulley, and it will be actually mostly about pulleys. So you will see it should be quite simple for you. Again, the procedure should be as always. I would like to ask you to download the test materials. Give yourself 1 hour time for solving as many problems as possible. And then you please stop your timer and your solution, please send to me either per email or by uploading it over Ilias system, or just take a photo of your solution and send to me, or make a PDF file and send to me, whatever you like. Just give me this feedback, and then I will use it as information where you need help or where you are, if you are already very good or you need some additional help. Okay, so please let us again use your test as a feedback, as communication between us. To finalize today's class, I want still to offer 2 little problems for you to solve, and after we've done it, the class will be over. Okay, so we have now only 2 little problems to solve. The test I will send today, actually more or less immediately after the class. So even if we finish a bit earlier, I will try to send it really as soon as possible, so that you get enough time. Sorry for that Fuad hasn't sent his test before. I know that the sooner you get it, the better. Yeah, so that's why mostly I'm doing my best to send it as soon as possible to you. Okay, let us check. Let us do these 2 problems, and then we will be ready. Sorry for maybe some inconvenience. Your screen may look strange at the moment. The reason is that since I'm using lots of monitors and screens, like a pilot in an airplane, my monitors are in vertical position. So that's why actually you are seeing my monitor, but it's in vertical position. That's why it looks strange. And that's why I'm using tablet, because it gives you normal look. But now, since my tablet is dead, I have to use my walking monitor, and sorry that now your screen looks strange. Yeah, so this is normal. It's not wrong with your screen. It is something wrong with my screen. Just a moment. I want to add. Okay, I think I can use this. Okay, first
one. Where's my mouse? Here.
there is a particle here, and it moves with some constant speed v. So particle moves with constant speed v. Sorry, now I'm drawing with my mouse, and that's why it is even worse than usual. There are two forces that act on my particle, F1 and F2. The force F1 is equal 2i plus and minus 6j. So this is in x direction, you know, right? This is in y direction. And the speed is, by the way, also a vector. My velocity is also a vector, and velocity is equal 3i minus 4j. The task is to find another force. What is F2? How much is it? Think about it a bit. I will repeat. Some particle having mass m is moving, we don't know m, is moving with constant speed v. Actually, v is the velocity, a vector, which is 3i minus 4j. The particle moves so because of action of two forces, F1, which is equal 2i minus 6j, and the second force is F2. And what is the second force? How much is it in I and in Z direction? So think about it. Yeah, thank you, but no, please don't try just to add or subtract these two vectors. Think about information I told you. And then it's very easy. Look, there is a particle that moves with constant speed. We need to assume that the net force acting on the particle is how much? Is 0, right? So because speed is constant, net force is 0. This is what first Newton's law says. That means that F1 plus F2 must be 0. Since F1 is equal to I minus 6j, F2 must be 0 minus F1. So it needs perfectly cancel the first force. So that's why F1 or F2 must be equal minus 2I plus 6j. That's it. So actually this 3i, 4j, blah, blah, this you don't need at all, right? So I have given it to you to confuse you a bit, to bring you from your concepts. But in fact, it's really easy, right? It's so easy if you just think clearly about this and use Newton's laws. Alles klar? Everybody got it? Yeah? I think it should be clear, right? So this is what we've started before. And now the very last problem for today. I hope you still have some energy. And this will be like this. Again, sorry for my handwriting. It is really bad, but so here's the pulley. And here's a rope. And on the rope, I have body A, B, oops, sorry, C, D. It's very bad looking, but I think you got the idea. So on the pulley, there are 4 bodies hanging. 1, 2, 3, 4. Okay. So now what I will tell you, the tension here is equal 98 Newton. And of course, since it's the same row, it is 98, 98, 98, 98 till here. So whole this part is 98. And here below, between A and B, tension is different and is equal 58.8. And between B and C, tension is equal 49. And between C and D, tension is equal 9.8 Newton. The task is to find the masses M of A, M of B, M of C, and M of D. And the whole system is at rest. Okay, so the whole system is at rest. Okay, please think 2 minutes long. How would you solve it? Please try to use the ideas that we discussed today. Imagine this is your midterm problem. How would you solve this midterm problem? Once this was a midterm indeed. So imagine now you are in midterm. How would you solve it? I give you some time. Let's say 2 minutes. Think about painter and chair problem today, painter and seat. It will help you. Okay, so I hope you got the idea, since we have 4 bodies in the system, and again, it would be very useful if for each body you first draw the force diagram. I did it for the body A and B, and you can do it for the rest of the body same way. So if I take the body A, let me switch to my laser pointer. There is an upwards force, which is tension, 98 Newton, pulling force of the rope. And there is another force downwards, pulling downwards. This is tension AB. And also downwards, we have a weight of A. So that's why we have our force diagram, and basing on this force diagram, we can write the equation, right? Which is tension minus TA. Tension is equal, no, I can do it this way. Tension minus TAB minus MAG equal to 0. Why equal to 0? Because it is at rest. Sum of all forces makes 0 acceleration. So that's why we can say T minus TAB minus MAG equal to 0. And I can find AMA. I'm slowly seeing that some answers are coming, very good. For the body B, we do same. Tangent in the upwards, tangent BC downwards, weight of it downwards. So we can write an equation TAB minus TBC minus MBG equal to 0. And we find the mass of B. And this we do for all other bodies. And so finally, you will get the answers. Yes, thank you for sending the answers. Yes, you're right. So if you did everything correctly, then the mass of your body A will be either 4 kilogram or 3.9 something kilogram, depending on your G value. Both is correct, both is fine. The weight of the body B, or the mass of the body B, will be 1 kilogram or close to 1 kilogram, 198 or 0.98. Body C will also weigh close to 4 kilogram, and finally body D will weigh approximately 1 kilogram again. Great. So our body is 4141. Perfect. You see, it works nicely, and even you have such lots of hanging bodies, using Newton's laws in a very systematic way, like step by step, helps you to solve even difficult problems. You notice the principle we applied. We split the whole system into parts. We analyze it. So this is the physical analysis, what we are doing here. We split it into pieces, and we split it into solution steps. And we do it step by step, and then it works nicely. Fine. Great. There was a question about the syllabus for the midterm topics. Sure, I will send to you. I think I have it somewhere. I have it from previous years, but basically it never changed. In the topics we need to have ready until the midterm are the whole kinematics, including projectile motion, the dynamics, that means application of Newton's laws and using pulleys and slopes and inclines. Then we need to have circular motion. Then we need to have conservation of energy and elastic energy and kinetic energy and work and power, of course. And finally, the conservation of momentum will be also part of the finals of the midterm. So we will need to cover all the topics from kinematics, including till conservation of linear momentum, including linear momentum problems. So this is what we're going to do in our class. So next week, we will discuss first your solutions in our test 6. Then we will talk about application of friction for problem solving. On the one hand, it's an easy thing, friction, but there are still some things that no one solves correctly, and there are always problems, always difficulties. I'm going to show some tricky places about friction that you need to know, that you need to be aware of. Okay, so that's why please come to the next class and don't think that friction is something easy. It is not so easy. So there are also some very complicated things about friction, which we need to discuss with you next time. So now the class is over. I want to thank you all for your attention, and I hope that from your feeling, I really hope that you got some more self-confidence. You learned how you address some problems, and some things became more clear for you. And please use this now for your homework solution, and so that we can go ahead next week. Thank you all. I wish you a nice week. And today I will send all course materials to you again. And see you next Tuesday, probably, right? Have a nice day. Goodbye.